All right, number 15 here, we're solving logarithmic equations. And this is the first of two types. So notice here we have log equals log. Anytime we have this situation, we're going to be able to set the inner parts equal, the 9 minus 2x and the x minus 3. So basically what we have is if we have the log base b of x equals the log base b of y, notice the x and the y, the only way that these two logs could be equal, since they're the same base, is if the inside parts are equal, or what we've been calling the answer. X must equal y here. And so that's what we're doing here. So again, I always say if you have log equals log, you set your inner parts equal. If log is equal to log, set the inner parts equal. So here 9 minus 2x is equal to x minus 3. We just need to get x on one side only here. We got 9 minus 3x equals negative 3. We need to subtract 9 on both sides. Negative 3x equals negative 12. And we're going to get 4. Now we do need to check these. If we plug in 4 for x, notice it'll be the log base 4 of 9 minus 2 times 4. That's 9 minus 8. That's the log of 1. And of course on the other side, 4 minus 3, we're also going to get the log base 4 of 1. So you can see that this does check. So with logarithms, you're going to have to check your answers because we've learned that you cannot take the log of 0 or a negative number. So when you plug in your x value, you got to make sure that you don't get some value that you can't take the log of 0 or a negative number. So on b, we're going to do the same thing because we have log equals log. So x minus 6 is equal to 4 minus x. Let's add x to both sides. Get 2x minus 6 equals 4. So we'll add 6 to both sides, and then you can see that x is going to be 5. But we've got a problem here because when you plug in 5 right here, whoops, 5 minus 6 would be negative 1. I can't take the log of negative 1. So there's no solution here. The other way to write that is using the empty set notation. Alright, so now letter C is very similar to what we just did. The only problem is we've got two logs on the left side. But we have a sum of logs. Well, we can use our product rule and change this into the log of a product. So let's do that. So we multiply the x plus 1 and the x minus 2, and we can make this into one log. On the other side, we just rewrite it. There's nothing to do over there. So now we do have log equals log. We can set our inner parts equal. We get x plus 1 times x minus 2 equals 4. Let's go ahead and FOIL the left side. You're going to get x squared minus 2x plus x minus 2 is equal to 4. So let's see, we have some like terms there, and we need to get the 4 on the other side. Because it's quadratic, we're going to need to have 0 on one side and everything else on the other. And so here we can factor this. So we need two numbers. We're using the AC method here. Two numbers that multiply to negative 6 and add up to negative 1. That would be negative 3 and 2. And so you're going to get x minus 3 and x plus 2, which means x is 3 or negative 2. Now, I can already see that negative 2 is going to be a problem here. If you plug negative 2 into that first log, it'll be the log base 3 of negative 1, because negative 2 plus 1 is negative 1. We cannot take the log of a negative, so we have to throw that one out. You can verify that the 3 does work. All right, on letter D, we have log equals log, so let's set our inner parts equal. So this is a rational equation. We need to clear fractions. So we're going to need, first of all, x can't be 1 or negative 1 because that would make us undefined. Our LCD is going to be x minus 1 times x plus 1. We have to treat these as two different algebraic factors. And so we're going to multiply each side by the LCD. And our plan is to clear fractions. That's why we do this. So to clear fractions, you just multiply each side of the equation by the LCD. So on the left, our x minus 1s are going to cancel, and you're left with 1 times x plus 1, which is x plus 1. And on the right, the x plus 1s are going to cancel, and you get 3 times x minus 1. So we're going to get x plus 1 is equal to 3x minus 3. We need to get x on one side only. And this is a two-step equation. We'll need to add 3 to both sides. And actually, you can see 2 times 2 would be 4. And, oops, let me go back. If you actually plug 2 in, you can see that it does work. All right, let's look at the next 4 of these logarithmic equations. So notice here we don't have log equals log. These are different. On the right side we have numbers, and so you can't just set the 5x plus 7 here equal to 5. This is a different problem, different type of problem. We have to notice what I wrote up at the top there, log base b of x equals y. That's logarithmic form. We can change this to exponential form. We know that b is the base, y is the exponent, and the x is the answer here. And so we just need to be careful and make sure we change to the exponential form correctly. So again, I like to use the round the world there. You go b to the y power equals x. So that's what we're going to do here. 2 to the 5th power equals 5x plus 7. And so that's 32 is equal to 5x plus 7. We'll subtract 7 on both sides. And you can see that x is 5 here. It's not too hard to check these. I'm just plugging 5 in for x. And you end up with the log base 2 of 32 equals 5. And that is true because 2 to the 5th power does equal 32. And so this one does check. Let's go ahead and look at f. Now notice on letter f we have a subtraction of 2 logs on the left. Well, we have a property for that. We can use the quotient rule. This will be the log of the quotient of those two numbers, 5x plus 1 over x minus 1. And that's equal to 3. So again, we're going to need to switch forms. We don't have log equals log like we did on the last slide. So it'll be 2 to the 3rd power equals 5x plus 1 over x minus 1. Of course, 2 to the 3rd power is 8. We need to clear fractions, so we'll multiply each side by x minus 1. So we get 8x minus 8 when we distribute on the left. And notice the x minus 1s cancel on the right, and we're left with 5x plus 1. So we're going to need to get x on one side only. And let's see, add 8 to both sides. And you're going to get 3x equals 9, which means x is 3. All right, so let's check that. If you plug that in, you're going to get the log base 2 of 16. That's 5 times 3 is 15 plus 1. That's 16. Minus the log base, let's see, 3 minus 1 is 2. And this needs to equal 3. Now remember, log base 2 of 16, what exponent do you put on a 2 to get 16? That would be 4. And what exponent do you put on a base of 2 to get 2? That would be 1. 4 minus 3 does, or 4 minus 1 does equal 3, and so that is correct. All right, on letter G, notice we have a sum of logs, so we'll use the product rule. So the log of base 2 of x minus 1 times x plus 1 is equal to 3. Again, we're going to have to go around the world here. 2 to the 3rd power equals x minus 1 times x plus 3. We're just switching to exponential form here. Of course, 2 to the 3rd is 8. And when you FOIL on the right side, you're going to end up getting x squared minus 1. So this is quadratic. We need to get 0 on one side. And so we get 0 equals x squared minus 9. And in fact, in this problem, you actually, you could use factoring, or you could take the square root of both sides, move the 9 over the other side. So there's really two ways to do this. I'm going to go ahead and factor it as I've done it here. So it'll be x minus 3 times x plus 3. So we're going to get 3 and negative 3. Well, you can see if I plug a negative 3 in, I'm going to get a negative answer. Like if I put a negative 3 right there, I'd be taking the log of negative 2, which I can't do. The 3, if I plug that in, I get the log base 2 of 2. 3 minus 1 is 2. Plus the log base 2 of 4, and that needs to equal 3. Well, log base 2 of 2 is 1, because 2 to the first power is 2. And the log base 2 of 4 is 2, because 2 to the second power is 4. And so that does work. All right. We've got one more. This one's very similar to the one we just did. You may want to try it if you haven't already. Or if you didn't get it right before, maybe now you can get it now that we did letter G. All right, so here we're going to multiply the x and the x plus 8, so we can turn this into one log using the product rule. On the other side we have 2. So let's go around the world. We get 3 squared equals x times x plus 8. That's 9 is equal to x squared plus 8x. And let's, since this is quadratic, let's subtract 9 on both sides. We get 0 equals x squared plus 8x minus 9. So let's go ahead and factor. We need two numbers that multiply to negative 9 and add up to 8. Well, they need to be opposites. 1 times 9 is what's going to work here. Notice you have to make the 1 negative in order to make this work. Negative 1 times 9 is negative 9, and negative 1 plus 9 gives us 8. So it's going to be negative 1 and 9 here. And we get 1 and negative 9 for answers. Clearly the negative 9 is not going to work. You put a negative 9 in here and you definitely have a problem. Can't take the log of a negative. And so just the 1, let's see, if we put a 1 in there, we get the log base 3 of 1 plus the log base 3 of 9. And that needs to equal 2. So what exponent do you put on a base of 3 to get 1? That would be 0. And what exponent do you put on a base of 3 to get 9? That would be 2. And 0 plus 2 does give you 2. All right, so we're good on that one. All right, so let's get into the formula problems. On 16, it says if you invested $25.60 into a savings account that earns 6.5% annual interest compounded continuously, so we're going to be using PERT here, how much would you have in the account after 22 years? And that'll be to the nearest cent. We're dealing in money here. So let's write down PERT. And we know the $25.60, that's our starting amount, P. Let's see, the 6.5%, that's going to be our rate. We'll write it as a decimal. Remember, you got to move that decimal 2 places to the left. And our time is going to be 22. So let's go ahead and plug in those numbers. So when you put this into your calculator, make sure that you're getting 10,697.47 or $10,697.47. So we made some money out of that. It says how much interest would you have earned? Well, since we started with $2,560, if we subtract that from what we have here, that'll tell us how much we earned in interest. So $8,137.47. All right, let's look at number 17. 30 years ago, Tom deposited $40,000 into a savings account earning 8.25% annual interest compounded monthly. So notice we're going to have to use the other formula here because this is not continuous interest. What's the value of the savings? Now round to the nearest cent. So let's go ahead and put our formula up. Let's see, the starting amount here is 40,000. It's 30 years ago, so T is 30. So P is 40,000. Our interest rate, of course, is 0.0825. So let's go ahead and notice it's compounded monthly, so that tells us that N is 12. Remember, that just means 12 times a year interest is being applied to the account. So let's plug in our numbers. We have 40,000 times 1 plus, let's see, R is 0.0825 over N, which we said was 12. And then it's the NT power, so 12 times 30. So again, once you want to make sure you're getting your numbers in the right place, but then it's just a matter of putting this into your calculator correctly. You get $471,260.22. So after 30 years, that money will grow quite a bit. This is the power of compounding. The only problem is it's hard to get interest rates like that these days. That's why so many people put their money into the stock market. Let's move on to the next problem here. It says, how long will it take for $3,000 to grow to $5,100 at an annual interest rate of 7.8% interest, or 7.8%, if the interest is compounded continuously? So how long, that's our time. Time is what we're looking for. Compounded continuously, we're going to use PERT. Notice the 3,000 is what we're starting with, and A would be 5,100. That's the amount that this is going to grow to after T years. And our interest is going to be 0.078 written as a decimal. Let's go ahead and plug our numbers in. And so this is the equation we have to solve for T. Now again, it would be just wonderful if we could just kind of ignore that 3,000. Then we would have a base, exponent, and an answer. We could switch forms, but we don't. So let's divide each side. We got that 3,000 there. Let's get that out of there by dividing each side by 3,000. When we do that, we get 1.7 equals e to the 0.078t. Let's change to log form now. So the base here is e. It's log base e of 1.7 equals our exponent, 0.078t. We don't normally write natural logs this way. We use ln of 1.7. So let's divide each side by 0.078. And when you put that into your calculator, you should get 6.8. So it's 6.8 years. Now let's double check this. It wouldn't be hard to do that. If we take 3,000 times e to the 0.078 times 6.8, that should equal 5,100. And you'll find that it does. And so this is a good answer. On number 19, it says you currently have $1,800 that you would like to invest. If you deposit it into an account earning 2.4% interest compounded continuously, how long will it take for your money to double? Well, we have continuous interest again, so we are going to use PERT. And notice the starting amount is $1,800, and the interest rate is 0.024. And if we want our money to double, how long? It's asking us how long it's going to take, so we're looking for time here. And how long will it take for your money to double? Well, we need 1,800 to double. That would be 3,600, just 2 times 1,800. So that's going to be our A. So let's go ahead and plug in our numbers. A is 3,600. P is 1,800. And it's 0.024 times t. So we're solving for t again. It's very similar to what we just did. Divide by 1,800 on each side. You get 2 is equal to e to the 0.024t power. Let's change to log form. And we should write this using the natural log notation. The only thing left to do here is to divide by 0.024. And so you get t is equal to 28.9. Now remember, this is the number of years. So notice the interest rate there is 2.4%. It takes almost like 29 years for that money to double. That's just amazing. So interest rates being low really makes it more difficult to earn money over time. So here, if we check it, you will see that it does equal 3,600, and so that's a good answer. All right, let's do this last problem, and then we'll stop this video. So it says in 1990, the population of a small town was 425. 20 years later, in 2010, the population was 485. The exponential growth function a equals 425 times e to the kt power describes the population A of the city t years after 1990. So this is our equation. Notice this tells us the population A of the city t years after 1990. It says find the growth factor k, round to 4 decimal places. So we must have been given the a and the t in order to find k. So let's see here. It says 20 years later, so the time is going to be 20. 20 years later, the population was 485, so that's what this, the 425 grew to 485. That's going to be your A. This formula is a lot like the PERT formula, if you haven't noticed that before. So 425 is like our starting amount, and 485 is acting as our A, and the PERT formula would act, or just like in the PERT formula. So let's see. Let's plug in our numbers. We have 485 for A, and T we said was 20. So let's go ahead and divide each side by 425. Now this doesn't come out to a nice number, so I'm just going to leave the 485 over 425 like it is. And now I'm going to switch forms. This is a base E log. And again, the exponent goes by itself. This should be written as a natural log. And we need to divide by 20. So go ahead and put that into your calculator. Make sure you hit, actually I think you could put it in just like it looks pretty much. And you get 0.0066. So if you checked it, 425 times e to the 0.066 times 20 should be about 485, and you can verify that that's true. So that's our k. So now we can write the formula with using 0.0066 for k. Now notice in B it says use the growth factor from part A to predict the population in the year 2020. Well, if you subtract from 1990, that was the starting year. Our time, remember time is number of years since 1990. This is going to be 30 years. So our T is 30. Let's go ahead and plug in our numbers. Actually, it's just the 30 and the K that we had found before. And when you do that, you should get 518. All right, and so we'll go ahead and stop the video here.